Hey, welcome back to Math with Patrick. Today is March 1st, and we have problem number 60 from this Daily Epsilon calendar to solve together. So today we need to show that this number, or I guess this fraction right here, looks like we have a huge number on top, dividing it by another huge number on bottom, apparently equals 1. All right, let's try it out. So one thing I know is that if I take like really any number and divide it by itself, I'm going to get 1. I mean, I guess this doesn't happen with 0. 0 over 0 is still undefined. There's no good answer for 0 divided by 0. But for any other number, if you take it and divide it by itself, you're going to get 1. So another way to reframe thinking about this is just to prove that, well, let's see, 1 cubed plus 2 cubed. Looks like I'm just adding up all of the cubed numbers from 1 to this current year. I just want to show that this is going to be equal to the denominator. And it looks like I'm taking all of my numbers from 1 to the current year again. But this time, instead of cubing each one, I'm going to add them all up first and then square it. So ideally, I could show essentially that the sum of cubes is the same as the sum of all of the natural numbers from 1 to 2025 all squared. So if we do this, if we see that they're equal to each other, it's the same thing as saying that this whole fraction is 1. Now, I'm kind of convinced that this upper number actually doesn't matter all too much. I'm guessing this would be true for any number at the top. So in fact, let's just try to prove the general version instead. 1 cubed plus 2 cubed plus all the way up to n cubed. And I just want to show that this is equal to, well, 1 plus 2 plus ... all the way up to n squared. So what's going to be really useful here are some formulas for adding up our natural numbers, adding up our square numbers, and adding up our cubes. And for now, it's kind of just like a trust me on this. Although if you wanted to do your own research, you could see why and how these these equations and these formulas work. So if I just sum up all the numbers from, let's say, n equals, actually, usually the incrementer number is an n, but maybe let's choose I. I equals 1 to n of I. So this notation right here just says take the number 1 and add it to the number 2, then 3, then 4, then 5, all the way up to n. And I'll write it all out. Why not? This says 1 plus 2 plus ... plus n. I actually talked about this in a previous video. I forget which day it is. But you can figure out that summing up the first n natural numbers is going to be the same as doing n times n plus 1 over 2. And then you can do the same thing when you sum up all the square numbers. This proof is a little bit harder, but there is a formula that's really, really well known. And you can do the same thing for summing up square numbers too. So it's going to look like 1 plus 4 plus 9 plus 16 all the way up to n squared. And this formula is going to be n times n plus 1 times 2n plus 1, all divided by 6. And then finally, there's another formula for the sum of cubes. I'm still going to do I equals 1 to n. And then this sum, if I wrote it all out, it's the same thing as saying like 1 plus 2 cubed, then plus 3 cubed, so 27, and then 4 cubed is 64. And we're just going to add up all of those cubed numbers up until n, my top number. Interestingly, this is actually the same as just squaring this one, n times n plus 1 over 2. Kind of neat. So if we apply these formulas back to where we were, well, on the left side of the equation, we have the sum of cubes. And going off of this formula, well, if I just have all the cubed numbers all added up till n squared, I could just replace it with that n times n plus 1 over 2, all of that squared. And that comes from this bottom formula here. On the right side of the equation, I see that I have all the natural numbers squared from 1 to n, all of the natural numbers from 1 to n summed up, and then I'm squaring it. So I'll deal with the square at the end, And then checking my formula for this sum from 1 to n, I'll just write n times n plus 1 over 2. And you might notice that I just wrote the exact same thing on both sides of the equation. I just want to be super clear where these formulas are coming from, so I'll color code it. This formula is coming from over there. And then this sum of cubes is just directly this formula from here. So basically, we're done. It doesn't matter that the highest value is 2025. In fact, it could be any number up there right here, and we'd still have something true. So let's just try it out, just like maybe the first two, see if it works. Well, okay, the first one is a little silly. That'd be like 1 cubed over 1 squared. And sure, that's still 1. So maybe let's try the next one that's a little less obvious. So it'll be 1 cubed plus 2 cubed on top. And then we would get 1 plus 2 and then square it later on the bottom. Well, that's 1 plus 8, so it's 9 on top. And then that's 3 squared, so 9 on bottom. Why not? Let's just go one further. Like, we already have proved that it'll work for any number, but it's kind of cool that it does. 3 cubed on top. Let's see, that'll be 9 plus another 27, so that's 36. And then amending the denominator here, I'll go 1 plus 2 plus 3 and then square it. That is 6 squared, and guess what? That's 36 still. So it seems like you could just keep counting up. This top number could be whatever you want, and every single time you're going to get the same number in your numerator and denominator. Therefore, dividing them both gets you a 1. That's it. We're all done. And we didn't even have to know what this big number was. Isn't that great? Don't even need to worry about that one. We know that something divided by itself will be 1. So, all done today. Thanks for coming along. I'll see you tomorrow. Bye.